Uh, okay. For the rest of the work, we can see that these normal equations that uh, led to find the estimate of b, and also y hat, which is equal to xb hat, can be obtained from getting derivative from sum of a square. Indeed, you can write the sum of the squares in this way. And if I get the partial derivative with respect to b, I can easily get to the normal equations. And this is just simple math that you can get the derivatives. Remember, it's a chain derivative because you can consider it's a function of b of another function of b. So we have g of h of b. So the derivative is j prime h times the derivative of h. That's why you get here this coefficient. The derivative is equal to 2, then minus comes from here, to this parenthesis, big parenthesis, and then the derivative inside the parenthesis, which is equal to xiv. If I get the derivative with respect to b new, element wise. Uh, Remember here from mass, since the summation is over j, you cannot get the derivative over j, and you need to get the derivative with another index. That's why we get the derivative with respect to b new. But okay, it's a simple mass, and you can from this expression you will get to the normal equations. You can also consider the normal assumption. Let me add a page. Suppose that once again you have y equal to x beta plus epsilon. I like to write notation beta. We usually assume that the error component has normal distribution with zero mean and sigma square I identity matrix. It's of dimension n. Remember that when you do the regression analysis, you need to conduct model checking. So regression diagnostic is needed when you take such an assumption. It's a distribution assumption. When you come to a distribution, then the likelihood comes in. So we will say that the likelihood of beta, which is actually a function of beta given x and y, which I can also write it as likelihood of epsilon. It is then given by 2 pi power n sigma power n, and then the expected value, the e power minus 2 sigma square, the error y x beta prime y x beta. The same thing as you have in sum of the squares. For sure, since it's a monotone function, I can get the log. So the log of the likelihood is proportional to minus 1 divided by 2 sigma square, y minus x beta prime y minus x beta. And you will see if you get the partial, if you get the derivative of the log likelihood, I write it just L of beta. With respect to beta, you will get the same result as the normal equations. So if I get the derivative and put it equal to 0, I will then find x prime x. Beta is equal to x prime y, which are the normal equations. Now let's look at the error space. If you remember from the previous video, which we discussed about the spaces, let's once again have this schematic representation. This this is the space, the regression space for VR. So it's what is this space? It's a column space generated by columns of X, which has rank equal to R. We can find another space orthogonal to it, which I can use this one, which we call it VE. And if you remember from the previous uh, video, we had Y, and then we did a projection, and this is and the projection was x beta hat, and here it is y minus x beta hat. So this VE, we said that y minus x beta hat is in VE, and x is beta hat is indeed in VR. And we discussed about uh, the dimension and degrees of freedom. Now here we go a little bit more and say let's look at the linear sets. So suppose that you have the vector space VE or small v or capital E, and it's defined as the air space, and the linear set is defined in this way. Instead of c prime y, here I have a prime y in order just to show that this is connection with the error. So this is actually the error set. And you see any linear function which the coefficient comes from this vector space. Then I can easily define the sum of the squares of LE, which we call it sum of the squares of errors. So whenever you are with errors, then you see us, okay, it's sum of the squares of errors. Or better said, when you work with the vector space generated by the columns which are orthogonal to the columns of X, R1. Remember, always. Sorry for this interruption. When you construct VR based on the columns of R columns of X, you're always able to find another vector space, another matrix, which are rated B1, B2 up to BR, which let's say this is the X, then x1 up to xr. I construct in this way, which b prime x is equal to 0, so it is orthogonal, and then you can construct VE based on the columns of B. Okay, so coming back, there's sum of the squares of errors, which we denoted by this, the sum of the squares of errors. Okay, this abbreviation here, it is given by this formula, and if you do simple multiplication, you get to this expression. So we have y prime y, and then minus y prime x b hat minus b prime x prime y plus b hat. Sorry, this guy must be b hat prime x prime x b. If I do this, then I can, of course, say this is the sum of squares of errors, and b hat is any set of least square estimators. Interestingly, the expected value must lie in that space. So once again, the expected value of a prime y is in VE, or this small e or capital A, and you can easily find it since e prime is a fixed coefficient, or it's constant coefficient, non-random. So it comes out from the expected value, and you can easily write it a prime, the expected value of y. But we already know that the expected value of y is given by xb, so expected value of e prime v e y is equal to e prime xb. Also, the expected value of a prime y is equal to 0. Why? Because these two are orthogonal to each other. Since they are orthogonal, so the expected value is equal to 0, and it is independent of b. So any choice for b which will give this result if and only if expected value e prime x is equal to 0. It means that the A prime y must be in LE, or better say the expected value of A prime y is equal to 0 if and only if E is in VE. But we already assume that, so we got this expected value equal to 0 at the beginning. Okay, thank you. It was a very short notice of video for explaining the rest of least square theory regarding the linear model, and also explain about the error space and error set and what happens in order to get the expected value equal to 0 for the vectors, which you understood that the vectors must be in VE in order to get the expected value equal to 0. Thank you.